So now we're going to get into a discussion of ionic sizes as measured by the ionic radius of an ion, all right? Which is different, of course, from the atomic radius. So here's a definition of the ionic radius. It is the portion of the distance between the nuclei occupied by that ion. So we're assuming, of course, that, a positive ion is in close proximity to a negative ion, such as in the case of magnesium oxide shown here. So the internuclear distance between the magnesium and the oxide ion is 205 picometers. The portion of that distance responsible, that the magnesium is responsible for, is 65 picometers, and the rest for the oxide would be 140 picometers. So that's basically how the ionic sizes are determined. Now, let's look at some trends that we'll observe when you compare the size of the cation, which is a positive ion, compared to the size of the atom from which they're formed. And what you're going to find, and this is without exception, that the cations are smaller compared to the atoms from which they're formed, right? And the reason for that is that as the atom loses an electron, which is, of course, is going to be the valence electron, then basically the nucleus will have a greater pull on the remaining electrons. In addition, there's less electron-electron repulsion, right? So if you compare, for example, the sodium atom here to the sodium ion, you see that it's almost decreased by half, right? From 186 picometers to 99 picometers. You see a similar trend when you compare magnesium to the magnesium ion, right? Magnesium, the atomic size is 160, and the size of the magnesium ion is actually less than half of that, which is 65 picometers. So that's basically the trend when you compare the size of the cations compared to the size of the atoms from which they're formed. Cationic sizes are generally smaller compared to the atomic sizes. Okay, then when we get to anions, it's opposite that is true. Anions are generally larger compared to the atoms from which they're formed, all right? And the reason why is basically when you add an electron to the atom, then you're increasing repulsion between electrons, and therefore the atomic size, or I should say the ionic size, will increase. Now at this juncture, I want to introduce to you a new term. It's called the isoelectronic species. Isoelectronic basically means the same electronic arrangement or the same electronic configuration, all right? So for example, before we get to that example, so going back to the relative sizes of the atom and the anions that they formed, here's an example. The chlorine covalent radius is 99 picometers, but the chloride ion is 181 picometers, so almost double the size. But back to the isoelectronic discussion right here. So you can have two species, two ions that have the same number of electrons, but the number of nuclear charges would be different. So a simple example of this would be when you compare, let me do this here. Let me get out of this here. When you compare, let's say, potassium ions to potassium ions to sodium ions, right? So if you compare the potassium ion to the sodium ion, right, you'll see that they both have 18 electrons, right? 18 electrons in both cases. But in the case of the potassium ion, it has 19 protons, and here we have, oh no, this is the wrong example, I'm sorry. I should be comparing potassium to calcium, so let me erase this here. So in the case of calcium, go back to this here. In the case of the calcium ion, which is Ca2+, it has 18 electrons. So they are both isoelectronic, right? They both have the same electron configuration because they have the same number of electrons, right? But the difference here is that calcium has 20 protons, right? So basically, calcium has a greater nuclear charge compared to the potassium. And therefore, as a result, the size of the calcium ion will be smaller compared to the size of the potassium ion. And that's because the 20 protons here would have a greater pull on the surrounding electrons, and therefore draw the electrons closer to the nucleus, and therefore decrease the size compared to that of potassium. So that's basically how we can compare the sizes of ions based on the number of protons present and based on the fact that the species may be isoelectronic, meaning they have the same number of electrons. Okay, so let me go back to the PowerPoint slide here and show you this table. And this table basically summarizes the trends that we covered so far in terms of the atomic sizes and ionic sizes of atoms and ions as you go across a period and down the group. So the purple spheres represent the atoms, right? The pink spheres represents the positive ions or cations, and well, maybe I misspoke. Hold on 1 minute. The blue spheres represents the anions or negative charges or negative ions, all right? So all that we have discussed previous to this in terms of trends in sizes, you can observe in this table. So if you look at the atomic size, it doesn't matter which period. So let's take period 2, starting with lithium. You'll notice that the atomic sizes decreases as you go from left to right, from 152 to 111 to 80 to 77 and so on, all the way down to 71 for fluorine. And then going down the group, let's say group 1A, the atomic size increases. So for lithium, at the top of group 1A is 152, then sodium is 186, and then it goes down to cesium, which is 265 picometers. And by the way, all these numbers here are expressed in picometers, all right? And then we can also see some comparisons in terms of the size of the atom to the size of the cation, which is formed from the atoms, I should say. So if you compare lithium to lithium ion, you see that lithium, the atom, has a size of 152. In the case of the ion, it's 59. And you see a similar trend when you compare pretty much all atoms and their corresponding cations. And then over here, when it comes to the negative ions, for example, oxygen is 73, the oxide ion is 140, so there's an increase. And the same is true for pretty much any anion compared to the atom from which they're formed. Just to choose an arbitrary example, if you look at iodide, the iodide ion is 220 picometers compared to iodine, which is 133, all right? And we can also see trends in terms of isoelectronic series. So for example, if you look at, let's say, calcium, potassium, and chloride, and sulfide, and phosphide, right? They all have the same number of electrons, all right? In fact, let me see here. In the case of potassium and calcium, they have the same number of electrons, but different number of protons. So one can see that the cationic size of calcium is smaller compared to that of potassium. Over here, if you look at phosphide, sulfide, and chloride, they have the same number of electrons, but the number of protons would increase going from left to right. So one can see that the chloride ion is the smallest because it has the highest nuclear charge, followed by the sulfide, followed by the phosphide, all right? So those are the trends that we can see clearly from this table. Okay, so let's look at this example. The question says, refer to a periodic table, but not to the previous figure. Arrange the following species in the expected order of increasing radius. So again, we're starting from the smallest to the largest. So what I'm going to do here is copy and paste this here to my writing pad right here. Okay, so let me bring this up. Okay. All right, so this is the question here. I'm going to minimize this and I'm going to bring forward the periodic table, make this smaller so we can have it to refer to while, hold on, let me see here. Okay, so the question says refer to a periodic table, but not the previous figure, and arrange the following species in the expected order of increasing radius. All right, so they gave you calcium, Fe3 plus, potassium, K plus, S2 minus, and Se2 plus, Se2 minus, I'm sorry. Okay, so the first thing I will notice here is that the calcium, and the underline is here, the calcium, the potassium, and the sulfide are isoelectronic, right? So let me just write them down here. Calcium, potassium, and sulfide. And the reason why I say they're isoelectronic is because they all have, in the case of calcium, 18 electrons, in the case of potassium, 18 electrons, and in the case of sulfide, 18 electrons, right? Now the difference is that in the case of calcium, this has 20 protons, potassium has 19 protons, and sulfide will have 16 protons. So basically, we can look at basically the nuclear charges to make arrangements in terms of the order of size. So it's going to be that calcium will be larger in size, will be smaller in size, I'm sorry, compared to potassium, which would be smaller compared to the sulfide. So at least for those three ions, we can determine the order in terms of the size. Now that leaves Fe3 plus and the sulfide ion, and the selenide ion to determine. Now, as far as the selenide ion is concerned, if you look at the periodic table, you'll see that selenide is below sulfide, right? Right? Selenium is below sulfur, so that means that selenide will be below sulfide, which means that the selenide ion would be of a larger size. So we can put the selenide here. All right. So the question now becomes, where will the Fe3 plus end up? Well, if you go to the periodic table again and you look at Fe right here, you see that the iron is to the right of both calcium and potassium. So what that tells me is that even with the ion itself, you'd expect that the ionic radius of Fe3 plus would be smaller compared to potassium and calcium. So going back to here, I would put the Fe3 plus to the being less in terms of the size, or smaller in terms of the size compared to calcium, right? So therefore, this would be the final answer to that question, all right? Okay, so the order would be Fe3 plus first, followed by calcium, followed by potassium, followed by sulfide, and then followed by the selenide. Okay, so we're going to stop here. The next topic we're going to discuss is trends with respect to ionization energy. All right, until next time.